For this lesson, we will be discussing about work, energy, and power. When a force acts upon an object to cause a displacement, it is said that work was done upon the object. Now, there are three key ingredients to work: force, displacement, and cause. In order for a force to qualify as having done work on an object, there must be a displacement, and the force must cause that displacement. So there are several good examples of work that can be observed in everyday life. For example, a horse pulling a plow through the field, a father pushing a grocery cart down the aisle of a grocery store, a freshman lifting a backpack full of books upon her shoulder, a weightlifter lifting a barbell above his head, an Olympian launching the shot put, and so many more. So every day we can observe work being done around us. Now, in each case described here, there is a force exerted upon an object to cause that object to be displaced. Therefore, there is a change in position. So when you apply a force on an object and it was displaced or it changed in position, work was being done on the object. Now, force mathematically is the product, work mathematically is the product of force and the displacement. So the equation is W is equal to F times S, where W is the work done, F is the applied force, S is the displacement. Like, for example, if you'll be looking at this figure, a man is pushing a car with force F, and as the man pushes the car, it changed in position from here going to the right, so it was displaced, S being the displacement. So therefore, in this situation, work has been applied to the car. So if we will try to compute for the work, then it will just be the product of the force being exerted by the man multiplied by the displacement S. So the unit of work is joule. It is 1 Newton meter. It means that 1 joule of work is done if we applied a 1 Newton force and move a 1 meter displacement. Now, the units of measurement for work for international system will have joule or Newton meter. For CGS is erg. Then for British it will be foot pound. Now, what if the force is not parallel to the motion? Because one of the requirements for work to be done is that the force should be parallel to the motion. Okay? So, just like earlier, when you look at the car, the force is parallel to the motion. If this is the force being applied, then the motion is parallel. Now, in this example, the motion and the force is not parallel to the motion. Now, how can we now compute for the work given the situation? If you'll try to look at our figure, if we will try to look at the free body diagram, the free body diagram of this would be, if this is the motion, the force will be the force is inclined but by a certain angle. So the force, for example, points to this direction. Let's say this is the force being applied and the motion is in this direction. Okay, at a certain angle, let's say theta. If this is the force, let's say force F, the only force causing the work is the force parallel to the motion. Okay, so what is the force? If we will try to break this into its component, it will have a component of this direction, F sub x, and in this direction, F sub y. So this is the components of force F. Now we only need to focus on force X, because force X is the only force that causes the object to move into this direction, into horizontal motion. So if we will try to compute for the work will be Fx times S, where Fx is F cosine theta multiplied by the displacement S. So this is the work done for an object with a force acting not parallel to the motion. So Fx is cosine, because if we'll try to use trigonometry, cosine theta, the adjacent side is Fx, and the hypotenuse, adjacent over hypotenuse, is F. Therefore, Fx is F cosine theta. Now, if you will try to notice, even on a straight motion, even if the force is not inclined, on a force horizontal or parallel to the motion, your angle will be equal to 0. But we all know that cosine 0 is 1. So actually, if the force is just parallel to the motion, you need not to use cosine theta or cosine 0, because it is understood that cosine 0 is 1. Okay, but if the force is inclined, we need to use this equation. But if the force is not inclined, the force is just parallel to the motion, then we need not use cosine theta. We can just compute for the work to be work is equal to Fs, or the product of the force and the displacement. Now, like for this example, find the work done if the force is 45 Newton, the angle is 50 degrees, and the displacement is 75 meters. So since the force is inclined, work is equal to F cosine theta times the displacement S. The force is 45 newtons, the angle is 50 degrees, and the displacement is 75 meters. Now, by just substituting all the given, we will find that the work done on the suitcase is 2,170 joules. Now, looking at this example, the work done can be a positive work or a negative work. Like in this example, the work of the man pushing up a barbell going up and then the barbell going down. So the work done of the man of the barbell pushing it upward is positive. It will just be equal to cosine 0 times S. Then the work done going down is negative. It will be cosine 180 degrees because the opposite of 0 degrees is 180. So therefore the work done going down is negative or negative Fs. Or we can just use the sign convention. Then if it is going up is positive, going down is negative, going to the right is positive, going to the left is negative. Now let us try to compute for the work done on this example. So the truck is accelerating at a rate of positive 1.50 meters per second squared. The mass of the crate is 120 kilogram and it does not slip. Now the magnitude of the displacement is 65 meters. What is the total work done on the crate by all the forces acting on it? Now let us try to solve this problem. Example problem, the crate. So let us first have the discuss the free body diagram. If you will try to analyze the crate on top of the car, the forces acting on the crate is just the weight of the crate going downward. Weight will be equal to mass times gravity. And of course, the normal force in accordance to Newton's third law. So the weight, and here comes the normal force, and the frictional force. The frictional force, Fs, is the force that prevents the crate sliding on the truck. So because of this force, the crate does not slip. So these are now the three forces acting on the crate, being on the accelerating truck. Okay. So the angle between the displacement and the normal force is 90 degrees. Okay. Let us try to elaborate this problem. So if this is the crate, the truck, we have now the weight, the normal force, and the frictional force going in this direction, static friction. Now the angle between the displacement and the normal force is 90 degrees. The motion is going in this direction. That is why the displacement also is horizontal. Then the normal force is 90 degrees relative to the motion. The angle between the displacement and the weight is also 90 degrees. So the weight is going downward, so it's also 90 degrees. If we are to compute for the work done of these two forces, work will be F cosine the angle, let's say theta, times the displacement. Now, cosine 90, F cosine 90 degrees times S will just be equal to 0 because cosine 90 is 0. Therefore, there is no work being done on the crate relative to the weight and the normal force. Therefore, the only force that causes work on the crate is your static frictional force. Okay? So, no work done is made by the normal force and your weight. Only the static frictional force. Now, if we are to compute for the static frictional force, the angle between the displacement and the friction force is 0 degrees. If we are to compute for the static frictional force, this is just equal to mass times acceleration. It is the mass of the crate times the acceleration of the truck. Now, the acceleration of the truck is 1.5 meter per second squared. Now, since the crate, the box is on the truck, therefore it has the same acceleration. So, the static frictional force, being the product of the mass of the crate and the acceleration of the truck, is equal to 180 newtons. Now, computing for the work of the crate being done by the static frictional force, okay, first erase this. Okay. So computing for the work, it will just be equal to F cosine theta S. But then if the force is just parallel to the motion, just like in this example, actually we can already omit cosine theta because cosine 0 degrees is just 1. So work can just be computed F times the displacement, and at this point it is the static frictional force times the displacement. The static frictional force is equal to 180 newtons. Even if we multiply it by cosine 0 is just 1. So this is just 180 newton times 65 meters. Then the work done is equal to 1.2 times 10 raised to 4 joules. Again, if the force is just parallel to the motion or to the displacement, we need not to put cosine of the angle because it is understood that cosine 0 degrees is just 1. Now, let us proceed to energy. Energy is a measurement of the ability of something to do work. So it is not a material substance. Energy can be stored and measured in many forms. One of the forms is kinetic energy. Kinetic energy is the energy of motion. An object that has motion, whether it is vertical or horizontal, has kinetic energy. There are many forms of kinetic energy, like vibrational, the energy due to vibration or vibrational motion, rotational energy, the energy due to rotation, and the translational, the energy due to the motion from one location to another. Now, the kinetic energy or Ke of an object with mass m and speed v is given by this equation. that kinetic energy is 1/2 mv squared. Now, consider a constant net external force acting on an object. The object is displaced at a distance s. So there is a change in position in the same direction as the net force. Now, the work simply is the total of the force, the summation of force times the displacement s, where the summation of force is equal to mass times acceleration times s. So this is an equation for work. So work, wait, let's erase. So from work equation, let us now derive the principle of energy from this work equation. Now, the work, if an object is displaced at a distance s in the same direction as the net force, this is the net force. Therefore, it is the summation of all the forces acting on the object. Now, work is the summation of force times s, where summation of force is equal to mass of the object times its acceleration times the displacement. So this is now the work acting on the object. Now, mass work is equal to mass times acceleration times the distance. If we will go back to our displacement, if we will go back to our kinematic equation, mass and the product of acceleration and displacement. This is, in our kinematic equation, displacement is denoted by x. So this is also ax. Ax. This is also equal to ax. Now, in our equation number 4 on kinematic equation, we have an equation of Vf squared is equal to Vi squared, or V sub O squared, V sub 0, plus 2ax, the product of acceleration and displacement. Now, ax, by deriving ax from this equation, is equal to 1/2 of the quantity Vf squared minus V sub O squared. So this is now ax. So we can now substitute ax to this term. So if we will go with we'll be consistent and substitute this value of ax to this, you will have m 1/2 times Vf squared minus V sub O squared. So by just substituting, by just distributing 1/2 m, we'll have 1/2 m Vf squared minus 1/2 m V sub O squared. But remember that mv squared, 1/2 mv squared, is your kinetic energy. Therefore, this is kinetic energy final minus kinetic energy initial. So the work energy theorem. So when a net external force does work on an object, the kinetic energy of the object changes according to this equation, that W is equal to kinetic energy final minus kinetic energy initial, or it is also equal to 1/2 mvf squared minus 1/2 mv sub O squared, or the initial velocity. Now, let us have this example problem for the work energy theorem. So the mass of the space probe is 474 kilogram and its initial velocity is 275 meters per second. If a 5.60 times 10 raised to negative 2 Newton force acts on the probe through a displacement of 2.42 times 10 raised to 9 meters, what is its final speed? So we are being required to find the final velocity. So the given are the mass of the space probe equal to 474 kilogram. The initial velocity v sub o or v sub 0, 275 meters per second. The force being applied is 5.60 times 10 raised to negative 2 Newton, and the displacement S is 2.42 times 10 raised to 9 meters. So we are required to get the final speed v sub f. Okay. Now let us look at the solution. Now, according to our work energy theorem, work is kinetic energy final minus kinetic energy initial. Therefore, our equation is 1/2 mvf squared minus 1/2 mv initial squared. But work, according to our previous previously to our discussion, this is the summation of force cosine theta times S. So ito yung work, summation of forces cosine theta times S. So we can substitute it to this W here in this equation. Okay. Now, summation of F cosine theta times the displacement is equal to 1/2 mvf squared minus 1/2 mv initial squared. Now, the summation of forces is 5.60 times 10 raised to negative 2 Newton. Now, since the force is just parallel to the displacement, then theta is 0 degrees. Cosine 0 degrees is just 1. So, kaya sabi ko sa inyo, kapag 0 ang angle, then cosine theta is just equal to 1. You can already omit cosine 0. Times the displacement S, 2.42 times 10 raised to 9 meters, equal to 1/2 times 474 kilogram, Vf squared, minus 1/2, 474 kilogram, the mass, times 275 meter per second squared, the initial velocity. Now, by just substituting all the given to this equation, we can get V final be equal to 805 meters per second. Or if you want, you can first derive for the equation for V final. So from this equation, we have F, summation of F cosine theta times S is equal to 1/2 mvf squared minus 1/2 mv sub o squared. If we will substitute this to the other side of this equation, this initial, we will have summation of forces cosine theta times S plus 1 half m v initial squared is equal to 1 half m vf squared. Now, we need to get vf squared, the equation for vf. Now, by multiplying it to 2, we'll have to eliminate 1 half on the other side of the equation. We'll have summation of f cosine theta times your displacement plus 1 half m v sub o squared is equal to m vf squared. We divide this by m, divide it also with m, cancel, so we have vf squared is equal to 2 times summation of forces times cosine theta times s plus, it's the whole quantity, plus 1 half m v initial squared all over m. But since this is squared, so v final is the square root of 2 times the quantity af cosine theta times s plus 1 half m v initial squared all over m. So we can have this equation to find for the final velocity. So it will just be depending on how you solve. So it's either you just input all the variables, then if you have a calculator, you can just shift solve for VF or derive an equation for VF and input all the given. Now another example is a 58 kilogram skier is coasting down a 25-degree slope. Near the top of the slope, her speed is 3.6 meters per second. She accelerates down the slope because of the gravitational force. Even though a kinetic frictional force of magnitude 71 Newton opposes her motion. So ignoring air resistance, determine the speed at a point that is displaced 57 meters downhill. So let us know the given for this problem. So a skier going downhill. The givens are the mass, the mass of the skier, which is 58 kilogram. Now we have the angle of inclination. Uh, 25 degrees. Now it says that near the top of the slope, her speed is 3.6 meters per second. So let's assume this is her initial velocity at the top of the slope. 3.6 meters per second. Then she accelerates down the slope because of the gravitational force, even though a kinetic frictional force of magnitude 71 Newton opposes her motion. So there is a kinetic frictional force of 71 Newton that opposes her motion. Ignoring air resistance, determine the speed at a point that is displaced 57 meters downhill. So the displacement is 57 meters, and we are being asked for the final velocity at a point 57 meters below. So when the skier reaches a displacement of 57 meters. So required is the final, or the speed at 57 meter mark, the displacement. So those are the given. So in this case, the surface is inclined by 25 degrees. So therefore, if you will try to look at our FBD, so this is the inclined surface, inclined at 25 degrees. So this is, let this be our arbitrary x-axis. So this is it, the x-axis. So we'll have the forces acting on the skier is its weight. This is the weight, mg. Okay. So if we'll have an arbitrary axis, let's say this is the axis with an angle of 25 degrees. Let's say it's the skier. We'll have a weight going downward, a normal force which is perpendicular to the surface, and the frictional force opposing the motion. This is Fs. Okay. So this is the free body diagram. Now if we will try to look at the forces acting, this is just the weight divided into components. This is the x component of the weight and the y component of the weight. So the x component is mg sine 25 and the y component is mg cosine 25. So let us first have a much clearer free body diagram. So let's say this is the inclined, 25 degrees. Let's say here's the skier. Here's now the weight. And the normal force Fn and the frictional force opposing the motion Fs. So the weight is divided into components because this is your weight. The weight is divided into components. This is Wy and here is your Wx, the x component of your weight. Now if you'll try to find for this component, if this is 25 degrees, then this is also equal to 25 degrees. So that is 25 degrees. So if you'll try to look for Wx, cosine 25, sine 25 equal to opposite. So this is the opposite side. If this is Wx, this is also equal to Wx. This is also Wx, this is also Wy. So if we will just project, so the opposite side is Wx, hypotenuse is W, therefore Wx is W sine 25. But W, the weight, is mass times gravity sine 25 degrees. So this is your Wx. Now if we will try to analyze our free body diagram, the motion is going in this direction on the arbitrary x-axis. Therefore, the only force that causes work in this example are the forces acting on the x-axis. And the forces acting on the x-axis is just the x component of your weight and the this is not static frictional force, but this is kinetic frictional force because the object is moving. So this is Fk. Sorry for that. This is Fk, the kinetic frictional force, not static. Again, let me correct myself. This is the kinetic frictional force because the skier is moving. So that is Fk. So the summation of forces at x-axis parallel to the motion of the skier is just equal to mg sine 25 going to the right minus the kinetic friction, the opposite direction. So that is why the summation of forces is equal to mg sine 25 degrees minus Fk. So those are the givens. Now let us look at the solution of getting the kinetic energy, the final velocity, because you are being asked to find the kinetic final velocity. Now, from the equation of kinetic energy final is equal to 1/2 m Vf squared, or the final velocity, by just deriving the equation for V final using the kinetic energy equation. So kinetic energy final is equal to 1/2 mvf squared. By cross multiplication, we will have 2 kinetic energy final mvf squared, then dividing both sides by m. So we'll have an equation for V final. V final squared is equal to 2 Ke, the kinetic energy final, all over m. And since the V final is squared, Vf is equal to the square root of 2 Kef, so Ke sub f, over the mass. So this is now our equation for V final. V final is the square root of 2 times kinetic energy final all over m. Now, if we will try to compute for using our work energy theorem, work is equal to kinetic energy final minus kinetic energy initial, or KE sub O, so that we can get for this kinetic energy final. Therefore, kinetic energy final, by just rearranging this equation, is equal to work plus kinetic energy initial. So we can now substitute this equation for kinetic energy final on our equation for V final. That is why V final will now be equal to the square root of 2 times W plus the quantity W plus kinetic energy initial all over M, because kinetic energy is equated to W plus kinetic energy initial. So we have now this equation. Now Vf is equal to 2W plus kinetic energy initial all over M. So work, we have now for work, according to our work formula, is just the product of the summation of force times the displacement. Now, the summation of force, according to our free body diagram, is mg sine 25 degrees minus the kinetic friction multiplied by the displacement. Now, again, if we will try to substitute this equation of work to our V final equation, V final is now the square root of 2 times the quantity mg sine 25 minus fk times s, our W, plus the kinetic energy initial all over m. So that is now our equation for V final. Now V final is 2 mg sine 25 minus fk, the kinetic friction times the displacement, plus the kinetic energy initial all over m. Kinetic energy initial can just be computed by 1/2 m V initial squared. We now have all the given on the equation, because we have the initial velocity, we have the mass, we have now the displacement, we have now we get now the summation of forces through our body diagram. So we can just simply solve for V final. So by just substituting all the given to our equation, V final is equal to the square root of 2 times the quantity mg sine 25 minus kinetic friction times the displacement, plus 1/2 mv initial squared, this is the kinetic energy initial, all over the mass. So we'll get an answer of 18.6 meters per second, or that is almost equal to 19 meters per second. So those are just sample problems for work energy theorem. So that is work and energy. So we're having a second part of our discussion, and the second part of our discussion will be our discussion on power. For now, this is the first part of our discussion for work and energy.